that this projective representation that I said, I mean, it's explicitly written in many places, but also they lead to honest representations of the modular group. And also the kernel that you have when you define the projective representation is very special. It's something called a congruent subgroup, so it's some special thing, and it's related with set n for this specific n, the order of the matrix. So again, it's a lot of number theoretical things that you can do because of that. And some other things that I didn't say, these S antimatrix are very powerful. Using the S antimatrix, you can compute a lot of things. For example, fusion rules can be recovered from the modular data using the Berliner formula. There is a formula that, using the S matrix and the dimension, the quantum dimension of the kernel that we define using the first row, which has the dimension of all the gives you the fusion rules. Then there is another equation that is called the balancing equation that relates twist and the S matrix with fusion rules and twist and quantum dimension. So there are a lot of things that you can do. And to call modular data, I was very fast. These are these two matrices that I define when you have a modular category. They give rise to two matrices that satisfies a bunch of things. So I'm not sure if they were the first, but in a paper, Brouillard, Richard Ng, Eric Rowell, and Shenhan Wang were proving a big result that I will tell in a minute. And they define what is modular data. So two pair of matrices satisfying a very big list of things, which we will not say, are called modular data. And one other question similar to the categorification before for fusion rules is, given two matrices satisfying all these actions, when there is a modular category such that their S antimatrix defined in this way are these two matrices that satisfies the correct conditions. Is always one or not? These are kind of questions that people also want to know. Yes.
I have maybe like physics-inspired question about these modular data categories, and especially about these modular isotopes that you mentioned. So, if you have two models that have all the same fusion rules, like in these modular isotopes, what is it physically that can still distinguish them?
No, a lot of things. The associativity is what it's distinguished. I mean, physically, physically is the 6J symbols, what is in this specific example changing.
Okay.
The associativity is different. For being Grothendieck equivalent, I mean, having the same fusion rules is one of the things that sometimes we are happy to get because being the same. So when we will talk about classification next, that's the next step, but classify fusion categories up to tensor equivalence, which will be the ideal. It's usually hard. So sometimes we are happy when we have a characterization, which I will say what I mean with that, or a Grothendieck equivalence, which means only same fusion rules. Of course, it's not super exciting, but it's something. But in that case, for example, the associativity, because as I said, the modular data is determining the fusion rules. So if you have two modular isotopes, they need to have the same Grothendieck ring, the same fusion rules. But the associativity is not clear how to encode it, and actually it's not encoded, as we can see in the example. So there is something, in that example, at least the associativity is not having in mind. So yes, there is much more to know about the modular data. I just wanted to mention some of the key things, but there are many things that you can do, and it's useful for the nodes and link invariants, and maybe later I will mention a little bit more, but I secretly set some of the conditions because I said that give right to the representation, but it's a little bit cheating. So. But I wanted to tell you about the classification program. That was something that, maybe just classification. So people have been studying a lot or trying to classify a lot fusion categories. Modular categories. Fusion categories are really hard to classify, as you will see in 1 second. And as I told you, what we do is we fix an invariant and we try to say as much as possible after we fix it. We decide different kind of things, and I can mention a couple. So the first invariant that I will talk is basically the first almost invariant that I mentioned when I defined the invariant, which is the rank. So the rank, the number of simple objects by rank. And this gets bad very quickly. So So rank 1 and rank 2 fusion categories were classified a long time ago by Victor Ostry. It turned out to be harder, so fusion, let me write here, fusion. Sadly, I have to say that that's what we know for fusion, rank 2, so the unit and 1 extra, it's kind of sad. This is by Ostrich. And he actually had to use braidings and modular categories. He had to go to the center of the category to do this classification. So up to rank 2. But then he added pivotal, which in principle, we're fine, it's a reasonable thing. And then he classified up to rank 3. And then people started working on modular, because in modular, as I said, you have much more stuff to play around. In particular, you have the S and the T matrix that have a lot of relations between them. So people started studying the modular case, and one big step was classifying modular categories of rank 4. There is a very nice work by Eric Rowell, Richard Stone, and Shenhan Wang, and they use the S and the T matrix, and maybe they start playing with the Galois group to classify modular categories. The Galois group that I mentioned briefly. So they start classifying in this way. So this work of many people, Rolliard, Ning, Rowell, I mean I will forget people, so Ostrich, and it's going wrong in the Shenhan Wang, Xiaowang Wen, many people here and more. And now there is a classification up to rank 11 in the archive. But Xiaowang put in Facebook the other day that they broke rank 12, so hopefully will be out soon, but I haven't seen it yet, but it's almost coming. Up to rank 11, but I have to say that here, a lot of the time, the classification is up to modular data. So they classify, what they do is, they find the S and the T matrix. Not always is up to ribbon equivalence. So we don't know. And the other thing is, a lot of the time what they do is they find the S and the T matrix and they find some realization, but then you need to know. So they find the S and T matrix and they prove if there is no realization, that's one thing, no realization, or they find some realization. Sometimes you want to know if there are more realizations also. So maybe there is a classification of modular data up to rank 11 for some things. Yes. One important result here, because if we're classifying by rank, a sensitive question that it was studied first or was posed first by Shenhan because he was actually interested, he said that because he was interested in the physical applications, he wanted modular categories. He wanted to know about rank finiteness. I'm not sure if I'm writing this word correctly, but rank finiteness, what it means. If I fix the rank, are there finitely many modular categories of that rank up to ribbon equivalence? Because if there are, it's more hopeful to try to classify by rank. If not, it will be wide, right? And the answer is yes for modular. This was proved by Brouillard, Ing, Rowell, and Wang, like 10 years after the conjecture. And then it was generalized to G-crossed, which I haven't talked about recrossed, braided, but maybe later I talk. But basically, it's not a braided category, it's something more relaxed than braided. You have something that it's a twist braid. It's using some group. You have some grading in the category and you have an action and some conditions. So it's not braided, it's a little bit less. So it's more than fusion. You have extra structure, but less than braiding. And this was proved by Corey Jones, Scott Morrison, Nikchik, and Rowell. Dimitri Nikchik and Eric Rowell. A couple of years after this one. But for fusion, it's open. We don't know.
Julia?
Yes.
Do you still assume in the Z-cross case that the trivial sector is modular, or?
No, braided. Only braided. I'm not saying G-cross modular, only G-cross braided. But for general fusion categories, we don't know. And in part, we don't know because one of the potential strategies was, okay, if I have a fusion category, and I know that it's true for modular, something that you could do is you could look at the center. But again, the center is a nice construction. We understand many things, but we don't understand how the rank grows. And Ettinghoff proved that even for these kind of examples like rep G omega, which is the center of something kind of easy, the rank grows crazy. So it's not like that trivial to prove rank finiteness from the rank because we don't have a bound, basically.
I'm just confused. If I set Z equals the trivial group, then do I get the same result for any braided rank finiteness for braided fusion categories? Not
yeah,
just
braided is true.
Okay.
For braided is true. This implies braided.
Okay.
Yeah, this implies for braided. I wanted to say this one because it's more general, actually, the G cross. But yeah, the first thing was for, they thought it for braided, but it's true for G cross. So for fusion, this is open. So what else we can say? I want to say more about classification by rank. But let me think for a second. So what we do to classify more by rank, I told you more or less what it's known for the general rank, with no other impositions. But a lot of people put extra restrictions to classify. So I will tell you this in a minute. I will go back because I want to do maybe some more details there. But I want to tell you, not much, but at least other things that people have studied, classification by other invariants, and probably I will not go in depth in that ones, and come back to this one. So other invariants that people studied, some of them I just mentioned without writing, are the quantum dimension, for example, things like this. So some of these results, actually, which I will mention now, are inspired by subfactors. So there is classification. This is for fusion categories because it's inspired by subfactors. So classification by bounding the dimension of, and these categories need to be special, of a generating object. So this is not for any fusion category, but if you have a fusion category that it's generated by one object, not as an abelian category, as a tensor category, you start tensoring and you take all the things there and you tensor generate. In that case, this is very related to subfactors. Basically, what you are doing is a classification of a small index of factors that are nice. And I don't remember what nice means now, but 2, 1, something good about subfactors. And there has been a lot of work on this direction. Afzali, Morrison, and Pennis have a very nice, I think, memoir article with that they studied this, Keineri, Mitchell, and many more people. And as I said, a lot of nice examples came from this side. Then other thing maybe also inspired more by diagrammatic categories, or because all these also have kind of planar algebra interpretation, so it's very nice and diagrammatic. Also other result that it's in this direction, but instead of bounding the dimension, what they bound is the multiplicity, multiplicities in some fusion rules. So what they do is they still have a category generated by one object, because again this comes from subfactors, and what they look is they do the square of the object and they want only to have some special kind of thing. So this is, I'm writing it very badly, but this is related to having trivalent vertices when you do a graphical interpretation of this, when you do the, and this, there is a very nice paper about this by Morrison, Peters, and Snyder. And then other things that people have done, classification by Frobenius-Perron dimension, but in the following sense, because I will talk about this also later, bounded the prime factors. should have it, because later we'll talk again about this. But so what I mean is that considering the dimension something like this, a prime to certain power times some co-prime element. And M need to be in these things square free. So no squares in the prime decomposition. There has been work by Don, Natalie Brulliard, myself, Eric Rowell, and more people, I think, Tucker, and more people. And this is for modular. Some results are for braided in general. Then there is some results about classifying by the quantum dimension of the category, but it's hard. So this is the quantum dimension, maybe I should. And this is for model, some of these are not for model, but yeah, B. And there is work by Shichuan Yu and Andrew Shupre. So there are many things, and one very nice that has, and if I have time, maybe tomorrow I will talk about this or not, depending. Okay, or maybe I will say two things, but one is looking at this Galois group. The Galois group of the modular category first was used as a tool to classify, but at some point, Richard Ng, and maybe I should write Ng, Elon Wang, and Qing Zhang, what they studied is the orbits of the action of the Galois group in the set of simple objects of your category. And they started studying what happens if I only have one orbit. And they have a very beautiful paper, and then there is some follow-up work on that. So number of orbits of the action. It gets hard very fast. Okay. Because the follow-up project was with Qing and Andrew Shupre and Shichuan Yu and myself, and we tried to do two orbits and get hard very fast. We couldn't do complete classification, but we could in the unitary case say a lot. And then some other thing that is interesting is studying the Frobenius-Schur exponent of the category, and we have some work with Andrew Shupre, Agustina Senki, that is here, and myself on this. But there are also some nice conjectures by Pavel and some other things. So maybe now let me go back here, because this is the one that I will say more. And it's, again, what we will do is we will restrict even more. We want to classify by rank, but we will impose more restrictions. So one restriction that we will impose is we will ask that the category is what we call integral. So for this, I will do an interlude and explain some things. And in this integral case, it's known up to rank 13 by work of Palku et al. So let me tell you what it's integral, and I told you something about Frobenius-Perron dimension, so maybe you can guess a little bit. So here we have the Frobenius-Perron dimension. So, okay, I wanted to do it differently. Let's write it here. So, I told you that in principle, the Frobenius-Perron dimension is some number, real number. So integral is already telling you that I want the integers to be there. But let's go a little bit slower. So one thing that I could have asked, erase it probably. Okay. So I don't know if you remember, but I said that invertible object means that the dimension or is equivalent to the dimension being 1. And we saw this Becky example, and we saw that example is nice in particular because in that case, invertible and irreducible were the same. So one kind of categories that we will consider are called pointed. These are definitions. And this is the same as the Frobenius-Perron dimension. Maybe I will write it like this. That the irreducibles of C is exactly the same as looking at the, maybe B, let's write. C is fine. The invertibles. So other way to say this is that the Frobenius-Perron dimension of xi is 1 for all I. Right? Because I said that any object is invertible if it has dimension 1. So I'm asking that all the symbols have dimension 1. And actually, these categories are very well understood This is a classical result, basically, by Heidelberg-MacLane, and this is well known. And all pointed categories are these ones that we looked before. Why? Because you can extract a group from here. You look at the irreducibles, you know that it's a group because that's the assumption. That group will give you this, and then you have a causality one. Okay? So in that way you can recover, and we prove that vice versa is also the same. So all pointed categories look like that. But maybe this is too much to ask, because we're asking that all the categories, all the simples have a 1. So we could relax this a little bit, and so we could say, okay, instead of that, we will ask that for all, maybe that the dimension of all simples, and instead of being 1, it's an integer. And actually, this implies the dimension of any object is an integer, because it will be a sum of integers plus multiplicities that are also integers. In this case, the category is called integral. Okay, so here we have pointed, integral, and we would like to have something nice also like this. And actually, we do. It was proved by Ettinghoff-Nikčika-Nostrick that integral is the same as having rep h here. There is a caveat, it's not Hoff, it's quasi-Hoff. Semi-simple, quasi-Hoff, finite dimensional. The same hypothesis that before. Semi-simple, maybe I should. Semi-simple, finite dimensional, quasi-Hoff algebra. So we understand very well integral. So when we study integral, like in this case that I wrote here, basically we're trying to understand Hoff algebra. So we have a nice characterization, but that doesn't mean that we understand them that well. Because actually there is not classification of all semi-simple Hoff algebra. So it's still very interesting and open and hard. But you could tell me, okay, but that maybe is too much. So if you have that this is true, the other thing that will be in an integer is this dimension. Because if all of these are integers, this will be an integer. So maybe instead of asking this, I will ask for weakly integral that is defined as the dimension of C to be an integer. So let me notice a couple of things. So of course, if it's pointed, it's integral. And if it's integral, it's weakly integral, because that's how we were relaxing the things, but not in the opposite side work. For example, I could take representations of any non-abelian group, and I will not get pointed, because I will have some representations with dimension bigger than 1. And this one doesn't work because, for example, I have Tambari-Yamagami categories. For example, Ising, if you compute the dimension of Ising is 4, but it has some object that has dimension as square root of 2, so it's not an integer. And that happens in general with Tambari-Yamagami. It's easy to compute more or less the dimension of the category. It's 2 times the order of the group, and the dimension of the X, the non-invertible object, is a square root of the order of the group, so many times it's non-integral. But in these 2 cases, I gave you a classification and a characterization. We would like to have something similar. The problem is that there is we don't know yet. But there is a nice conjecture by Ettinghoff-Nikčika-Nostrick from 2009 approximately, that it says that weakly integral comes from groups. So I'm being very sloppy here. And I will be more precise, but I want the groups. Comes from groups for me will be something that is weakly group theoretical. So for this, I need to give you a lot of definitions, so I will do it in a minute. But what I mean is, weakly group theoretical, since it comes from groups, is very nice. It's nice to work with a weakly group theoretical because you have all the group theory for you. This is nice to find because finding the dimension of the category is easy. Knowing if the category is weakly integral or not is easy. But knowing if it's group theoretical or not is harder. So it would be nice to know if they coincide or not. If they coincide, it's great because we will have a lot of results and proof that they are conjecture that they are true. On the other hand, if it's false, it will be very nice because it will be more wide. But what we know, maybe we do know something about this weakly integral. If this is the case, so if the dimension of C is an integer, this thing that happened for Tambara-Yamagami or for Ising is not an exception, it always happens. The dimension of the simples are not necessarily integer, but the square are. So we have something. It's not, so basically the dimensions are square roots or integers, okay? Like it happened in Ising that we saw that. So let me give you some definitions to explain the conjecture a little bit better, and then I will give some results of classification with restrictions on the dimension, even more than integral, or kind of related to integral. I will explain in a bit. So maybe let me say what I want to say now. So pointed, as we saw, is just being back to omega. So there is a notion that I mentioned before but I didn't explain, which is the one of Morita equivalence. To be honest, I want to cheat and I will give an equivalent definition that is not always true, so it's a little bad, but in our setting it's true. But if you change characteristic, if you go to non-semi-simple, if you go higher, in all the other settings fails, but in fusion categories over the complex or algebraically closed fields of characteristic 0 work. So C and D, fusion categories, are Morita equivalent, which I will write just an E. If and only their centers are equivalent as braided fusion categories. Again, I didn't define the Drinfeld center. I kind of assumed that people knew it. If not, I will define it later when I speak about, or I might not. I was going to skip it actually, but if you request, you can tell me, and I will explain. But it's this construction that you give me a fusion category, I will give you a braided fusion category. Actually, it's not the generic. So you want these two things to be equivalent. So being pointed is this, and there was this definition of group theoretical fusion categories that I think of Nixie-Canoster gave, that it's Morita equivalent to pointed. For that reasons, I will not go further on this, but there is a very concrete description of this category. It looks like, oh, it's Morita equivalent. Remember that the center of pointed, just to remind ourselves, even if you don't know what it is, I told you that it's a very well-known co-algebra. It's this twisted group, twisted Drinfeld double of the group. So it's well-known. People have studied a lot of this. This group theoretical can be described very nicely in terms of this and some extra data. H will be a subgroup. This will be some other cohomology data that restricts well or leaves well or something like this. Basically, what it's a group theoretical category. It's some category of bimodules. So you pick some algebra in this category, and then you take bimodules there. So it's very concrete. I'm not describing it, but it can be very concrete, and there is a lot of work studying these categories. In the braided case, moreover, it's nicer because in the braided case, it will be a subcategory of this category. And Naidu, Nikshik, and Witherspoon studied the subcategories of large. So there is a parametrization. So now I wanted to mention two words that I will use later. So I will use, I already use weakly group theoretical. I think it's called weakly group theoretical because first they define group theoretical and then they realize that weakly group theoretical is also important and it's related to group, but the name was taken. So weakly group theoretical, just because we are in this mode, we will define it as Morita equivalent to something that we call nilpotent. I know that this is not good because we're adding and adding definitions. But because fusion categories are very closely related to groups, a lot of the things that people studied for groups, then they try to study for fusion categories. In particular, there is a notion of nilpotency and one notion of solvability, which I will introduce in a second. So let me say what is nilpotent. There are many ways to define nilpotent, or some ways. I like another one better, but I don't want to introduce the notation, so I will use this one. Basically, if you have C, a fusion category, C bar is an extension of C by G, and this is important because I will use it all the time later, so it's good that we introduce extension. If there is some, so if this C tilde can be decomposed using my group like this. This will be just full abelian or no, this will be, yeah, no, I will decompose it as a direct sum of things. I can decompose this C tilde, this new fusion category as a sum of components. This will be full abelian subcategories of this one. And I want some things. First, I want this to behave well with the tensor product, because I have a group structure and I have the tensor product. I want them to be compatible. Second, I say this thing is an extension of this thing, so I want this thing to happen somewhere. And where it happens, the trivial component is my C. And usually, and I will say this later, so it's good, what I say is, oh, C tilde is G graded. For being an extension, I want all these components to be non-zero. I want something that really needs the whole group, not that I could pick a different group. It's a bigger category. I'm extending my category, okay? Would be a nilpotent. So C, I use all the letters. So my category C is nilpotent. It's a different C than this one. If it can be constructed from like you do an extension of other extension of other extension, so, consecutive, no, what would be a good word? Okay. From extensions of VEC. So you start with VEC and you do an extension. And you keep going. If you do an extension of VEC, yeah, maybe I will not say that, but yes, you will get something related to groups, that's why. It's sequential extensions of VEC. There is a different way to say it, which I like it more, but this one is a little easier for this. So weakly group theoretical means that the center of your category is equivalent to the center of something nilpotent. And the last definition that I wanted to give, because I will use it for some conjectures, is solvable, which is kind of sad now, but we will do it, means that it's Morita equivalent to a cyclically nilpotent category. What means cyclic is that all the groups that I'm using for my extensions, all the groups that I'm extending by, are cyclic groups. And actually they can be picked cyclic of prime order. So here I'm picking VEC. If it's nilpotent, it's because I pick it VEC, and I did an extension by G, and then an extension by G1, and then an extension by G2, and then by G3, and like this, of the resulting thing, right? Now, cyclic nilpotent is the same, but the GIs need to be set PI for some prime PI, okay? One thing is that solvable implies weakly group theoretical. If you are solvable, you are also weakly group theoretical, because that's more restrictive, it's asking more, right? So now, I will give you some results that are inspired also on this, plus some group theory, so that's why I wanted to mention these things. So, as I said, there is this classification by PyQ up to rank 13, but this is more or less new in the last couple of years. But this problem of classifying integral modular categories was started earlier studying some Egyptian fractions and things like this by Paul Bruglia and Eric Rowe. And in that paper, first of all, they leave some question, or they mention some question like, oh, they starting studying some categories that are integral, and in particular, they starting studying, so C is a modular category, maybe B, modular category with Frobenius per own dimension an odd number. They starting studying odd dimensional modular categories. When the category has odd dimension, for free, the category is integral. Having odd dimension for free gives you integral. You will need to believe this. I can give you reference later, or I can mention this later. But if it's odd, it's integral for free. So this is a family of integral modular categories. They started looking at this problem, and in this setting, these restrictions are the same as having that B is maximally non-self-dual. So what this means? A category will be self-dual if every time that you have an object, the dual is isomorphic to that object. So all the objects are isomorphic to the dual. Maximal non-self-dual is the opposite side. But I cannot request that any object is non-isomorphic to the dual because the unit is always isomorphic to itself. So this means that if xi is simple, one of my simples, and it's isomorphic to its dual, then it needs to be, maybe I will write I need to be 0, meaning that xi needs to be 1, right? So the only simple at itself dual is the unit, because that's always required, okay? This is very useful to study this. So in the early times, they study this problem and they give a classification up to rank 9. And then the other thing that they did is they found an example in rank 25, which is related to this family, which I probably raised, of Minier and Schauenburg. It's also some semi-direct product of things, of these cyclic rank groups. And that one was, so up to rank 9, they proved that was pointed. And in rank 25, because of this semi-direct product is non-abelian, it's non-pointed. So they wanted first to know if there was some odd dimensional modular category with rank between 11 and 25 that was not pointed. That was one of the questions. The other question they mentioned is that they wanted to know about group theoretical. How, if they always, because all these examples I'm mentioning are group theoretical, the center of pointed categories by definition group theoretical, right? So the answer is no. There is some categories that David Jordan and Eric Larson studied that I usually call Jordan Larson. I don't know if it's a good name, but these are extensions and they're very nice categories, kind of a generalization of Tambaré-Yamagami, and they show that there are odd dimensional that are not group theoretical. So you could take the center and you will have also non-group theoretical odd dimensional. So odd dimensional doesn't imply group theoretical, but we have nice results about this. So maybe let me tell you a little bit about, so these things here imply a lot of things. If you have a modular category, the square of the dimension of a simple object divides the square of the dimension of the category. This is only true for modular. So if you have an odd dimensional modular category, all the simple objects, and all the simple objects will have dimension odd. So from here, all the xi are odd dimensional. So that's something nice. So with Agustina Senki, we started studying this problem, and we made some nice progress. And then with Agustina Senki and one other student called William, and the last name is hard, that's why I'm trying to pronounce it, but it's hard, Bodyak, I think, but probably I'm mispronouncing William's last name. We advance a lot the classification of odd dimensional by rank. And for that, we prove some nice things. For example, we prove that, with Agustina, we prove that the rank of C is congruent to the dimension of C mod 8. This follows basically from this. Because mod 8, all these squares will be 1. So when you're counting the dimension, you're basically counting how many simples you have, which is the rank. And this is very useful because when you're classifying by rank, you know this. And that gives you a lot of restrictions here, and you can play around many things. So with Agustina, basically what we did was working toward answering Brullial and Rowell question. So we were able to see that most of the categories up to rank 25 were pointed. There is one only category that is not pointed, and it's related to these Jordan-Larson categories. You can construct it tentatively taking some equivalentization, some things with the Jordan-Larson categories, but maybe I will not go in detail there, but it's in rank, I think, 17, that one, I don't remember. But basically, we know how they behave up to rank, here, up to rank 23. And then with William, we studied this up to rank 73, but here there is a big sign that it's not, so partial results only. But something that I found very interesting on the work that we did first with Agustina and then with William is that, okay, I will delete maybe this, but there is this conjecture by Tinkovnik, Chikanostrik that tells you about this weakly integral. And we want to know if the weakly integrals are all group theoretical or not. But for many years, this conjecture has been stopped because probably we need some new tool. And I think this classification started giving some ideas on where to look at. Not like we know what to do, but basically, for groups, you have this Fay-Thompson theorem, which is a very, very famous theorem, that if a group is of order odd, then the group is solvable. And I told you in categories, solvable implies weakly group theoretical. So during my PhD, I proved with my advisor, Sonia Natale, that if you start with a weakly group theoretical, so if C is fusion weakly group theoretical, and the dimension is odd, then C is solvable. And many people get super excited and are like, oh, you get a new proof of Fay-Thompson, which is like 100 pages long. I don't know, it's very long. And I'm like, no, we really use Fay-Thompson for this because we started with something group theoretical, and I told you that basically that means that comes from groups. So you can use what you know for groups. So no, we didn't prove it. But basically, when we were doing this classification results with ours, we saw, so in the work with Agustina and the work with Agustina and William, we saw basically that in many cases, we found a class of categories that we couldn't discard. Discard or prove they exist. We couldn't discard or prove they exist. And we call these categories perfect categories. And I will say why this comes from groups also, not because they are perfect in any way. So the idea is that I told you that one very important group is the group of invertibles. That if you give me a fusion category, I can attach to it the group of invertibles. In the modular case, this group even has a lot of implications. This group of invertibles give you a grading in the way that I told you. It's very strong, the group of invertibles. So perfect means that the group of invertibles is just the unit. It's as small as possible. That's the definition for perfect. Okay? So then, why this is important? For a couple of things. So Ettinghoff, Nikchik, and Ostrich generalize the result for groups. For groups, you know that the only solvable imperfect group is the identity, the trivial group. So what they prove is that C fusion, if C is not vague, which will be the trivial one, and is solvable, then the group of invertibles cannot be 1. So, in other words, C is not perfect. So why I got super excited in some sense is because we were working with odd dimensional categories, and in principle there is this conjecture in general. I was mentioning this case with Sonia. The natural question is, can we remove or not this? So basically, proving that you can remove this would be like a Fay-Thompson for fusion categories. Proving it for fusion categories or modular categories is the same by taking the center, so it doesn't matter if it's fusion or modular. But basically, what we check with, or what we prove with Agustin is that looking at this conjecture for the odd dimensional case is equivalent to this weakly group theoretical for the odd dimensional case. So actually, looking for perfect or proving that they don't exist could be a way to prove the weakly group theoretical conjecture for at least part of things. And actually not only for the odd dimensional, because the follow-up work that we did was working with modular categories of dimension that it's not divisible by 4. Why that? For many things. One, it's inspired by group theory because perfect things start appearing when you have divisibility by 4. But the other thing is because a lot of the good things that we had here, the integrality is not only for odd, it's also for not divisible by 4. So if here, 4 doesn't divide the dimension of this, I also get integral. And all this is also true implies all this. I mean, maybe this is in general, but I mean this part. The dimension of the object is still odd because I need a 4 to have any chance to have a 2 in this side, and then this other conclusion also. The only thing that it's very different is the maximal self-duality, because I told you that it's equivalent to odd. So with Agustina and Akshaya Chakrabarty, we studied modular categories with dimension. The case that we were not studying with William, basically, that is complex with 2 mod 4. So it's not odd, but it's also not divisible by 4. And in that case, we could give so the case with William, we gave a lot of partial results. We can't say when it was pointed or what case it could appear. A case that is very complicated is when the dimension is a perfect square. That's why 25 is hard, because it gives a lot of possibility for perfect. But this case, we could give like a closed answer. In this case, it's always equivalent to V tilde times V set to Q. So let me tell what are these ingredients. This will be a non-dimensional modular category. And this is a modular category of rank 2. Maybe pointed modular category of rank 2. You could also have Fibonacci if I don't say pointed. So it's always split. Basically, understanding these ones, it goes down again to odd. And then this result that it's proved here actually also, maybe I should change it, can be generalized for not divisible by 4. Instead of that, can be upgraded. But we still, so basically this also shows that a very interesting class is looking for existent or proof that it doesn't exist perfect categories of odd dimension. And then understanding the case when it's divisible by 4 gets much wider. starting by that if it's divisible by 4, this is not longer true. For example, easing has dimension 4 and has a square root. Still, you could restrict to integral, but things get changed a lot. And maybe just an insight on how we prove this is what I was telling you. The main thing here is that these are maximal non-self-dual. That gives you a lot of things. So we wanted to know how far from maximal non-self-dual this was. And basically, we proved that there were 2 simples that were self-dual, the unit, and 1 extra invertible object, which is here. So that's what we did. And I think I'm already on time and past on time, so I will stop here and we'll continue tomorrow. If you have any questions, you can also ask me. I'm sorry that I went over time.
This is a small one. I got a bit lost. So to drop the weakly group theoretical, you need to show that that there are no perfect categories.
I mean, that would be a way to prove it. If you prove that perfect cannot be odd, you will prove this Phaeton for fusion categories.
Would that tell anything about the
It will
group
tell you the
theoretical?
weakly group conjecture for odd dimensions, or for not divisible by 4. So if you prove that perfect cannot exist when the 4 doesn't divide, then you will have this conjecture proof for things that are not divisible by 4. So it's for this class of fusion categories. Still, there will be all the others, but for this conjecture, you need integral. That's why also it's important, because since it's for this conjecture, it's weakly. Yeah. We are only doing the integral, basically, and also a little bit more than half of the integral. You have the dimension for divisible.